your STEM 10 Plus series. I am Archie and I work at UC San Diego CREATE. Today we're going to be learning about Archimedes Principle. We will learn about the history of the principle and how it came about in ancient Greek, how it was discovered by Archimedes. And also we're going to test that this principle holds true. And afterwards we're going to also do a demonstration that applies to engineering, to modern marvels, and where we use this fundamental principle to create wonderful things, like for example cargo boats. So we're going to get ready to talk about the materials that we're going to be learning about today for our experiment. You might see here that in the counter that I have multiple materials, but we're not going to use all these materials at home, okay? So what I have here on this side, you're going to be using at home, okay? You're going to have a bucket that's shallow, about a foot in depth. You're going to need some aluminum rectangular foil sheets. You're going to need either pennies or beans, but I don't have pennies or beans, but I have these little teddy bears that's going to help me out for my experiment. If you can see, just small little teddy bears that I can account for it later on. Also, you're going to need sufficient water. You're going to need towels because this experiment is going to get messy, and you also want to wear clothing that you're okay with getting wet, and you want to work in an area where it's okay that if you get wet, you're okay to clean it up, and that way your parents won't get mad at you. And what I have here on this other side, I have a vase filled with water, and I have two Coca-Cola 20 fluid ounce bottles. One of them is filled with sand, and I have a scale. This is going to be the experiment to test out Archimedes Principle. Okay, the purpose of this science lesson is to really understand the principle of Archimedes. Once we know how to use Archimedes Principle, we can definitely use it to our advantage. For example, we can use it in different kinds of fields. One of the fields that we can use is in engineering. We can create amazing modern marvels like cargo ships that we see right behind me. And then raises that question, like, how does this monstrous boats float in a liquid, right? So back in ancient Greek, there was this king, Herod II, who ordered somebody to build them a crown made out of gold. And the guy made a beautiful golden crown, but then there was rumors in town that this guy had cheated the king, that he took some of the gold that the king had gave him and swapped it with some silver. And the king was pretty upset, but he was also a fair man. So he hired his brilliant cousin Archimedes, which he was a phenomenal, brilliant mathematician, to solve this mystery. Archimedes had no idea. He was taking a bath, and all of a sudden, when he went into the bathtub, he saw that water was being displaced out of the bathtub, and that's how he figured out how to find the volume of an irregular shape. And he started yelling, "Eureka, Eureka, I found it, I found it." And with this, he went to the king and solved the mystery that indeed that person that the king had hired definitely cheated him. So now that we learned about the little history of the Archimedes Principle, let me tell you the definition that Archimedes definitely stated. Any object totally or partially immersed in a fluid or liquid is buoyed up by a force equal to the weight of the fluid displaced by that object. And let me show you a little diagram here that I have here. For example, you might think this is the object in red, and there's a buoyant force that's acting on this object. Also, like how we were saying, if it's fully submerged, there's also a buoyant force acting on it. So we're gonna go ahead and verify this experiment that it holds true. So remember, it's equal to the weight of the water. Okay, now that we have heard about the Archimedes Principle, now we want to test it if it holds true. So what I have here, I have a flower vase, and it's filled with water. I have my scale. I have two 20 fluid ounce plastic Coca-Cola bottles. One of them is filled with sand. And what I have done with some scissors, I have cut the wrapper, but you don't have to do it. I just did this so you can see what's actually going on. So first, what I want to do is go ahead and weigh this bottle with sand. See how much it weighs. It reached 546 grams. So afterwards, I'm gonna go ahead and put it into the system of water, the fluid, and you can see it's dancing. It's dancing. It's not fully submerged, but it's partially submerged, just like how Archimedes Principle have stated. So if you can see very closely, I don't know if you can see, but how the water level of this bottle with sand, where it stops. It's really important. You want to see that. Okay, and then you have definitely see that the water has definitely displaced up. So I'm gonna test it again. Displaced up, it went up. So now what I have here with this bottle is gonna be useful to collect how much water was displaced by this sand bottle. Okay, let me clear as much as water I can, dry it off. So now what I'm gonna go ahead and do, fill it up. Let's see, come over here so you can see a better angle. Okay, let me put the lid to this. And I'm gonna go ahead and, after I put the lid, I'm gonna go ahead and let it dance here in the vase with water. So you can see how it floats. And as you can see, it kind of floats in the same region where the water marking, the water level of the bottle with sand was floating as well too. And let's compare. So which one, here's a question for you. Which one do you think is more dense here? The sand or the water actually is inside here? As you can see, it requires a little bit less sand than it requires water to float at the same level. But now let's go ahead and try Archimedes Principle. Okay, so it says that the buoyant force that's pushing up on the object is equal to the mass of the water displaced. So let's say if it holds true. So let me recap on this. The weight with the bottle with sand is 546 grams. Okay, so, but let me go ahead and tell you before I weigh this. This is a very technical experiment. So if we're like +5 or -5 grams, we are okay with that, because every little drop that you miss or that you fill, it's gonna definitely count for an error. So let's go ahead and weigh it. So we're at 542.2 grams, and that's pretty close. So I'm happy with that. So that proves Archimedes Principle. But also let me tell you something. So when we did let me go place the water. So when we started, what these markings are. What these markings say is that originally at this mark, we had the water level that it wasn't disturbed, and then when we partially submerged this bottle, it got displaced to the mark on top. But then how do we know how to collect how much of the same water that it was displaced? Well, what we measure a piece of paper to signal that this was the same amount. So if we take this bottle out, it's gonna go back to the original location. But then what we did, we equally subtracted the amount that we needed to be displaced, which that was gonna tell us that Archimedes Principle was gonna hold. So definitely, this is a cool experiment that you can do at home. Okay, so now that we have tested the Archimedes Principle, that it holds true, now we want to go ahead and apply it in an engineering aspect, in the engineering way, and where we have to be creative and really apply this principle to use it to our advantage. Like how I was talking to you earlier about the cargo ships that we saw, or the cruise ships that we saw outside. So in order to do this at home, go ahead and grab your bucket, fill it up with water like how I did, and leave about 2 inches from the top. Go get your pennies or your beans that you're gonna be go ahead and use it as cargo. Here I have my teddy bears, and then go ahead and grab an aluminum rectangular foil sheet. And you only need 1 rectangular foil sheet, okay? So don't go ahead and grab 3. Just go ahead and do 1, because everybody wants to be grabbing many, and then that's gonna take the whole creativity of the engineering critical thinking aspect. So go ahead and just use one. Like I have used one, and the camera guy has used one. This is the camera guy's boat. His name is Nate, by the way. Say hi to Nate.
Hello.
So go ahead, and then this is mine. So I did a small one because I feel like Nate's not gonna float. That's what I'm saying. So now let's go ahead and test it. So I'm gonna go ahead and test Nate's first. Oh, I was wrong. So Nate did a good job at applying Archimedes Principle. So his boat is actually floating. So that's really good. Just similar how we saw the Coca-Cola bottle with sand, that it floated. It didn't sink all the way to the bottom. Let's look at mine. So mine floats as well. So I did a good job. I really understand Archimedes Principle because the buoyant force that's pushing up from the water and the weight are equal. So that's the reason why they are floating. So now I'm gonna go ahead on my cargo. You can go ahead and add your pennies. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 9. And use another one. 10, 11, 12, 13. Oh, at 13, it started sinking. It started picking up water. So at home, go ahead and try and see how much cargo or pennies or teddy bears you want to use. So now I'm going to go ahead and test Nate's boat and see how it works. It's okay for the sirens. There's some sirens going off, so don't be alarmed. So just doing this home video, and there are sirens outside. So this is Nate's boat. This is good. So mine hold at 13. So I'm gonna go ahead and test his. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh wow! So he already surprised me. Wow, Nate, you have done a good job. So let's put 5 more. Okay, so it seems like it's holding up. So he has done a really good job at designing a really good boat. And I want to go ahead and encourage you that if your boat doesn't really hold as much cargo like how mine, don't be discouraged. Go ahead and try again. Grab another aluminum sheet and try again. And think about this. Think about this question. As an engineer, you always want to think about this question. How can you do it better? How can you improve? So in this case, I have to really go back to the drawing board and think about like my walls. My walls were pretty small. My boat was pretty small too, so it couldn't hold a lot of cargo. So look at Nate's. Nate's has pretty good walls around it, and he has a nice little base that he could put more teddy bears if you like. Let's see. Okay, and it still floats. So he did a good job of applying Archimedes Principle, and his design was really fabulous. So go ahead and challenge your cousins, your brothers, your mom and dad to see who has the better design to test for this. And that's Salem right there if you haven't really seen him around the video, but this is his house, so we gotta acknowledge that and respect that. Pretty wonderful cat. But I also want to go ahead and recap on what we learned today. So we learned today about Archimedes Principle, how Archimedes found out to test for that crown that was really, really bad design by the person that the king hired, and he got cheated. And good job for Archimedes for taking out that challenge. And also we tested that principle, and it definitely helped out. It worked out. We did a good job on proving that it did work. And then now we have done this. We have created an engineering aspect to the principle, and where we have designed boats that you see out there when you go to the port, when you go to Super Village, and see them all over San Diego. And I want to say thank you for joining us at this video. Thank you for staying in tune. Go ahead and wait for the next lesson to pop up, because we have a lot of science videos that we want to share with you. We want to share this knowledge to you now that you're at home with your education. I want to say thank you and see you soon.